Okay, I'm back, and in the previous segment we were discussing what was it that causes the tides and how the strength of the tides is going to depend on the mass of the planet, so the Earth. It's going to depend on the mass of the moon, and it's going to depend on the distance between them. And so we also found out that if the moon was to get closer to the Earth, then the tidal force would become stronger and the oceans would rise higher to meet the moon. And then we also found out that according to Newton's third law of motion, the Earth must also be pulling on the moon, causing it to stretch. So let's look at it from the point of view of the Earth. And then here's the moon over here. And then the tidal effect would cause the moon to do this. It would begin to stretch. And so if we could take the moon and move it closer to the Earth, the stretching factor would get stronger and stronger. So if we go to our next slide here, we could find that eventually there would be a certain distance from the Earth at which the force that's stretching the moon would be stronger than the force that's holding that moon together, and then it would be ripped apart. So that distance at which that occurs is going to be called the Roche limit. So whenever a moon gets inside the Roche limit, then the tidal force is going to be stronger than the force holding the moon together, and it's going to be pulled apart. Well, we could actually calculate that, and so there's a couple of formulas there for actually being able to calculate the Roche distance. And so in the box down there below, I give some typical Roche limits based on the mass of the objects involved. So the first one is, what would be the Roche limit for the Earth-Moon system? So the formula says that we need to know the mass of the object that is in the middle, and then the mass of the object out here, and then we also need to know the radius of the moon. So I looked all of that information up. I found the mass of the Earth, and I found the mass of the moon, and I found the radius of the moon, and I plugged it all into that top formula, and I found out that the Roche limit for the Earth-Moon system would be about 18,000 kilometers. So the moon would have to get 18,000 kilometers away from the Earth, and if it got any closer, it would be pulled apart. Now, where is the moon? The moon is actually 384,000 kilometers away from the Earth. So do we need to worry about it? No, the moon's not going to be ripped apart. Now let's look at Jupiter and its moon Io. So I plugged in the mass of Jupiter, plugged in the mass of Io and the radius of Io, and I came up with the Roche limit of 127,000 kilometers. And then I looked it up and found out its actual distance. So the actual distance between Jupiter and Io is 422,000 kilometers. That's pretty close. So those two numbers, the 127 and the 422, are fairly close to each other. So that means that Io is almost on the verge of being pulled apart. And we're going to find out later when we talk about the moon Io, it's very, very volcanically active. And we're going to find out why later. And it has to do with this Roche limit. And then just for the sake of argument, I did it for the Sun and Mercury. Do we need to worry that Mercury is going to be pulled apart due to the gravity of the Sun? So its Roche limit turns out to be 1 million kilometers, but it's actually located 35 million kilometers away from the Sun. So yeah, you don't need to worry about it being pulled apart. Okay, so that is how the tides can destroy a moon. And so in our next segment, we're going to talk about how can the tides influence the rotation rate of a moon and the rotation rate of a planet and the distance between them. Okay, so I'll see you in just a few moments.